Okay, good morning. So in the previous class, we have done this numerical problem, which is on vapor absorption refrigeration system, and here we have actually uh, we have used the ammonia water mixture. Okay, so ammonia was refrigerant, and water was as absorbent. Okay, and for these given conditions, we tried to represent all the states on the enthalpy composition diagram, and after representing all the states, we were able to determine the enthalpies, and then we estimated actually the COP of the system, and also we established that there is energy balance even if we neglect the pump work. Okay, so first law is being satisfied. So then COP we found as 0.1013. Then after this simple vapor absorption efficiency system, for the same numerical problem, I gave you another variant, and the variant was that whenever this strong solution is supplied to the generator, before entering the generator, it is having actually heat exchange in the preheater with the weak solution coming from the generator. And the given state was that at the exit of the preheater, the temperature of strong solution is 40 degree Celsius. Okay, so those who have solved this problem, the COP, final value of COP, because if your COP is correct, it means all your enthalpies and estimation of heats are correct. So the value of COP I have as per the answer is 0.22. So your value is point how much? 0.22, correct. Then the third variant was that now we will be having this heat exchanger also along with that, because in order to operate the expansion valve in the safe limit, our interest is always to achieve certain amount of subcooling. Okay, so we will be doing some subcooling after the condenser, and whatever the fluid is coming from the refrigerant is coming from the evaporator, that is passed through this subcooling heat exchanger. Okay, and here the condition was that after the refrigerant mixture coming out of the subcooler, then it is in the pure saturated vapor state. Okay, so did you try this? Okay, maybe you can give a try. If you have some doubts, that we can discuss in the next class. But here COP will be 0.3048. Okay, so you can see the now the benefit of using these additional components. Okay, so earlier what was happening in the previous system, original simple cycle, we are not using any preheater before generator, we are not using any subcooling. So COP was 0.1. Once we started using the preheater before the generator, our strong solution was partly heated in the preheater itself, and the amount of input which we need to supply in the generator, that has actually reduced. So that's why my COP has become 0.2. But after that, in the third case, COP has again increased to 0.3, because in this case, when I have done subcooling, then subcooling has actually resulted in significant increase in the specific refrigeration effect. So once specific refrigeration effect has increased, then even COP has further improved. Is this point clear? So what are the reasons for increase in COP in the two cases? These also I briefly told to you people. Okay, so what I want is that if you have not tried these questions, so what you do, please refer to the previous lecture, because in the previous class many of you were not there. Please refer to the previous lectures. These are very important problems, and these problems cover all the concepts of the vapor absorption refrigeration system which we discussed till today. Okay, so that's why these are important problems. Please practice these. Now we will study certain challenges. If, what are the challenges if water enters in evaporator? What is the meaning of this? Okay, The meaning is we have some device called generator. What we are doing in the generator? In the generator, strong solution, that is from pump, ammonia plus water is coming, okay, and we are heating this strong solution with the help of hot fluid, okay. So over here we are adding heat. Now what happens with heating? With heating we get that ammonia first evaporates, okay. So if ammonia is evaporating first, then from the top I will be having actually here ammonia coming out of this, ammonia vapor, okay. But from the previous numerical problems, you might have observed that these problems were actually corresponding to the actual practical conditions. Okay, so you have observed that whenever ammonia entered over here, it was not pure vapor ammonia, because what was the value of composition? X value. What was X value? Whenever we observed from the enthalpy composition diagram, we found that X was close to 0.94. Okay, what it means? It means that along with the ammonia, of course significant amount is 94% is ammonia, but small amount of water has entered into the condenser. Is this point clear? And after this, again it will actually enter into the expansion device, and then from expansion device it will enter into the evaporator. Now what are the issues if water goes with ammonia in the evaporator? What are the challenges? Can you tell me? First important point is, always in the evaporator we try to do the heat transfer process under the constant temperature conditions, so that we can maintain our refrigerating space at the given temperature conditions. Is this point clear? But if I have the mixture of ammonia and water entering over here, can the heat addition process be constant temperature? It cannot be, because for a pure substance, addition of heat within the saturated liquid vapor states results in change of phase. But for mixtures, even if it is entering in the saturated state, then also along with the phase change, temperature also changes. So first issue will be happening that temperature of evaporator will increase upon addition of heat. Is this point clear? Now, earlier what was the situation? Earlier the situation was that evaporator temperature was remaining constant, say to some value Te. Now evaporator temperature, say at inlet fluid temperature is Te1, at exit evaporator temperature is Te2. So now comes important point. First point is, if you operate with the same pressure condition, it means evaporator pressure, whatever was there with pure ammonia, same evaporator pressure you are maintaining with water and ammonia mixture. Okay, in that case what will be happening? For the mixture, always evaporator temperatures will be higher in comparison to that for pure substance. Okay, so first point is Te will increase upon addition of heat, so we will not be able to maintain constant temperature. Second point is, for same evaporator pressure, okay, for same evaporator pressure, my evaporator temperature will be more than pure ammonia system. Is this point clear? So what it means? It means that you will not be able to achieve the required refrigeration effect if you operate at same pressure. Okay. So what you need to do then? You need to decrease the pressure, because ultimately refrigerated space is something which is our requirement. Okay. So I cannot change my output if my system is not behaving properly. But what I need to do? I need to make the system behave as per my requirement. Okay. So requirement is same. So I should maintain TE temperature. So in order to maintain TE temperature, I must ensure that this exit temperature must be either equal to in a limiting situation or less than TE. Then only I will be able to maintain my refrigerated space. If this goes above the specified TE temperature, then I will not be able to achieve my given task. Okay, is this one clear? So that's why third important task is that PE dash evaporator temperature has to be maintained very less in comparison to PE, which is required for pure system. Okay, a very simple comparison you can take, that whenever with X equal to 0.94 with 94% of ammonia in your numerical problem, you have seen that when you maintain the evaporator at 0 degrees Celsius, your required pressure was how much? 1.75 bar. But if you go to the saturated ammonia table, and from there you can check the value of pressure corresponding to 0 degree Celsius. So corresponding to 0 degree Celsius, the pure ammonia pressure is how much? 4.29 bar. You got my point? So it means that if pure ammonia would have entered in the evaporator, then the evaporator can be maintained at a pressure of 4.29 bar. But when 94%, it means 6% of water has entered, then your evaporator has to be maintained at a temperature, at a pressure of 1.75 bar in order to maintain the evaporator at the same temperature conditions. Is this one clear? So what will happen with this? Your PE has decreased. So it means the PE to PC ratio will increase pressure. So your system has to be operated at significantly high pressure ratio. Okay. So once you will be operating the system at high pressure ratio, ultimately it will be resulting in decrease in COP. Okay. So COP of your system will be decreasing. There are two things. Of course, pumping from evaporator pressure to condenser pressure will not make any change because pumping work is typically negligible. But what is making change over here, across the expansion device you are doing expansion from PC pressure to PE pressure. Okay. So if your pressure ratio across expansion device is large, it means there will be more amount of flashing. So if there is more amount of flashing, this specific refrigeration effect will be decreased. Is this point clear? So this point you have to understand very carefully. Again I am repeating it. Increasing pressure ratio in case of vapor absorption system is not decreasing COP, so that you will be requiring more work input for pumping from low evaporator pressure to high condenser pressure. But because that work is almost negligible, but it is decreasing because whenever across the expansion device you will be doing large expansion. So from saturated state, if you do expansion, more we go down, more we move away from the saturated liquid state. It means there is more amount of vapor formation because of flashing process in the expansion. Okay. So this will be decreasing significantly our specific refrigeration effect. Is this point clear? So specific refrigeration effect decreases, which results in significant decrease in COP. Other thing what can happen? Exit temperature is almost same. So as such, on generator heat also there will not be any significant effect. Okay. Okay. What is next? Next is very important thing.
Water will be liquid state in evaporator, which is
Yes.
difficult to do.
Yes. So the point is, whenever a mixture is entering in the evaporator, evaporator is having some tubes. Okay. So water generally upon addition of the heat, ammonia will evaporate first. So significant amount of, after certain use, I will be finding that significant amount of water will be collected in the evaporator. So water will try to stay in the evaporator itself. So water, what can happen if you are going for very low temperatures, Water can even freeze also, but that we can control with the pressure as well. But other important issue is it will try to significantly cover the most portion of the evaporator. So what we need to do after some routine use, either we have to make certain arrangement, mechanical arrangement with the help of which I can take out the water which is collected in evaporator, or second thing is I have to choose the evaporator tube size in such a way so that the velocity of ammonia vapor is very high in the evaporator, and this high velocity can carry water in the form of droplets. Okay, so velocity of ammonia vapor should be maintained high. Why? To avoid water accumulation in evaporator. Is this part clear? Anyone is having any doubt about this? So it means that though this cycle seems very interesting, that it is only taking waste heat, and based on means it is only taking heat which I can even get from the many waste heat sources, and it is giving me some useful refrigeration effect by not consuming high grade energy. Okay, but these are certain challenges. So how to avoid these challenges? What we need to do, we need to perform ammonia enrichment process. Okay, so how to perform an ammonia enrichment process? I'll give you one simple example. I'll take this idea from a simple example which we already discussed. If you recall, I have explained you one process which was cooling and separation. Okay, so if I have some saturated vapor, if I do cooling, and after cooling, say I have done cooling from 1 point to 2 point, and then I have done separation. So upon separation, what will be happening? Liquid and vapor will be separating out, but temperature will be same. So if I have some isotherm passing through this point, then this will be my liquid, this will be my vapor. From this vapor, if I further do cooling and then again do separation, I'll be having some state 6 and 7. So here you can see that my vapor is actually trying to move towards the higher concentration side. Okay, so cooling and separation process will lead to formation of rich ammonia mixture. Okay, so now we will employ this particular process inside some mechanical arrangement for enrichment of ammonia. Is this one clear? So how we will do enrichment of ammonia? Let's try to see. So this is my generator. What I will be getting at the outlet of the generator? Ammonia plus water vapor. My desire is that I should get pure ammonia vapor, but as I told you that from the exit of the generator, I will not be always getting pure ammonia vapor, but along with ammonia I will be getting some amount of water vapor also. Is this one clear? So ammonia plus water vapor is entering from the generator. Okay, but say this is my state. Okay, let me write it as like this only. Okay, so this is ammonia plus water vapor. Now what I will do, in the top I will use one heat exchanger coil, and in this heat exchanger coil I will keep on passing the cooling water. So whenever this cooling water will interact with the vapor coming from the bottom, what it will do?
Water will cool that.
This was ammonia and water close to the saturated state. Okay. So out of this vapor, some amount of vapor will start condensing. Is this point clear? Will it condense or not? Okay. So what will first condense?
Water.
First, of course, water will condense, but it is not always true that it will be pure water only. Along with water, there can be some ammonia. So what I will be finding that here I will be having formation of some liquid droplets on this. Okay, and these liquid droplets, because of the gravity, these will fall in downward direction. Is this point clear? Now once these liquid droplets are falling in downward direction, this liquid below this heat exchange portion we have a long vertical column, and in this vertical column I have multiple plates, parallel plates, baffles. So through these baffles my liquid will try to move in the downward direction. Is this point clear? And while this liquid is moving in the downward direction, whatever the ammonia and water vapor is coming from the bottom, because of its lighter density, this vapor will try to move in the where? Upward direction. Okay. So what will happen? At each plate, there will be some heat exchange in between the vapor and the liquid. Okay. Vapor which is coming from generator will be having higher temperature, and the liquid which is coming from the cooling coil, it will be having low temperature. So this liquid will try to get certain amount of heat from the vapor. So partly some condensation of vapor will take place even here itself. Okay. That's why this particular column is something which is called as rectifier column. Okay, this is called as rectifier column. What is happening in rectifier column? In rectifier column, some amount of water is water vapor is getting condensed, and I am getting more and more. So basically this type of process is happening. You see, in the first plate, water and vapor has interacted. Whatever the vapor has condensed, that has been separated and that has started moving in downward direction, and the remaining vapor has moved in the upward direction. It means this type of small multiple cooling and separation stages are being performed in these plates. Is this one clear? So this is called as rectifier column, and the top portion where we are doing cooling with the help of some external cooling medium, this is called as Dephlegmator, or it is also called as reflux condenser, or sometimes in general sense reflux heat exchanger. Is this point clear? So this is Dephlegmator or reflux condenser. Okay, and this is nothing but my rectifier column. Now what I will be getting at the exit of this, I will be having now state 3, which is nothing but my state at the inlet to the condenser. So I will not use only generator. After the generator, I will use this rectifier column and Dephlegmator. Okay, which will be further helping us in ammonia enrichment process. But out of this also, I will not be able to get 100% pure ammonia. Okay, my ammonia composition at state 3 will be 0.995 to somewhere close to 0.998. Means I will have significantly pure ammonia, but not exactly the pure ammonia. Very small fraction of water will still be there. Why a very small fraction of water will still be there? Okay, maybe first I'll discuss few more things, then I'll explain this point. Is this point clear? And now out of this, what is coming out? Liquid. Means of course it will be reach concentration of water, but it can have some amount of ammonia as well. Okay, so liquid is moving in the downward direction. Now let us mathematically understand this process. Physically I explained you, okay, but if you have to design the dephlegmator, how you will be designing? Okay, so if you have to mathematically understand this process, for that purpose let me take a simplified control volume of the combined dephlegmator cum rectification column combined system. Okay, so this is my dephlegmator and this is rectification column which is having multiple plates. Okay, if I take control volume across this is the control volume. In this control volume, what are mass and energy interactions? First mass interaction is that some mass is going out at state 3, so m dot 3 is the mass flow rate. And of course composition over here will be x3 and enthalpy will be h3. Is this point clear? And other thing is, from the bottom some vapor is entering and that vapor is entering with m dot v mass flow rate, xv composition and hv enthalpy, and some liquid is going out with m dot l flow rate, xl composition and hl enthalpy. Okay, and in terms of heat interaction, what we have? We were having some cooling coil, okay, which were taking heat outside. So we are removing some QD amount of heat in the dephlegmator. Is this point clear? Anyone is having any doubt about this? Now let's consider I have selected for my analysis an arbitrary plate where the corresponding liquid and vapor have compositions XL and XV. Is this point clear? I have taken arbitrary some random plate where XL and XV are the compositions of the liquid and vapor which are interacting over this plate. Is this point clear? Anyone is having any doubt? Okay. Now what is the purpose of the plates? The purpose of the plates is that whatever vapor is moving from the bottom, that should transfer some amount of heat to the liquid which is falling from the top. Is this point clear? So it means that the temperature of the vapor has to be greater in comparison to temperature of liquid at that particular plate. Are you getting this point or not? Okay. Vapor temperature has to be greater than liquid temperature, then only heat transfer will take place. What it means? It means that at a particular plate, my liquid and vapor phases are not in equilibrium. Okay, so usually during the two-phase transition, what happens? When you have liquid and vapor phase, in the separation tank, the temperature of both liquid and vapor was same. But in this scenario, the temperature of both liquid and vapor is not same. So that's why, because if vapor has to transfer heat, then its temperature has to be greater in comparison to temperature of the liquid. Is this one clear? Okay. Now, let me first write the mass balance. What will be mass balance? Please tell me. Mass entering is m dot v, going out is minus m dot l minus m dot 3 equal to 0. From here I can simply write that m dot l will be equal to m dot 3 minus m dot v. Is this one clear? Other thing is, sorry? Okay, V minus 3. Okay. Other thing I can write the composition balance. What I will be getting from composition balance? Minus m dot L XL minus m dot 3 equal to 0. Fine. Now let me substitute m dot L over here. So what I will get? M dot V into XV minus m dot V minus into XL equal to m dot 3 into X3. Now keep it also on the left side. Now take out the common as m dot V. So if you take m dot V common, you will be getting XV minus XL, and if you take m dot 3 common, then what will you get? XL minus equal to 0. From here I can get that m dot V by m dot 3 is equal to X3 minus XL. Correct? Is it okay? Or have I made some mistake? Sorry, XL minus?
Instead of XL minus X3 should be X3 minus X.
Okay, here it should be X3 minus X. Okay, so is it correct? This is my ratio of m dot V by m dot 3. Now let us do the energy balance. What will be energy balance? M dot V into HV minus m dot L into HL minus m dot 3 into H3. Anything else? Minus of QD, because that is also heat going out. Okay, equal to 0. So from here what I will get? Let me divide this equation throughout by m dot 3. So I will get m dot V by m dot 3 into HV minus m dot L. M dot L by m dot V, what I will be getting? 1 minus m dot V by m dot 3. Is it correct or? Let me replace it in a usual manner. Okay. So what I will be getting? M dot V minus m dot 3 into HL, correct? And divided by m dot 3, correct? Minus of m dot 3, 3 cancel, H3 minus of QD divided by equal to 0. Okay. So from here, if I take m dot V by m dot 3 common, I will be getting HV minus HL, and m dot V by H3 I can replace with this. So X3 minus XL divided by XV minus XL into HV minus HL, and this minus minus will become plus HL minus H3 minus QD by m dot 3 equal to 0. Anyone is having any doubt about this? From here I will get HV minus HL divided by XV minus XL times X3 minus XL equal to H3 minus HL plus QD by M dot 3. Okay. So this is my equation. All of you are clear? This is nothing but my equation which I can apply on Dephlegmator and the unit. Now how this equation is applicable for each and every plate, because in the rectification column we have multiple plates. This I have written for entire control volume, but it should be applicable for each and every plate also if I just only take simple plate as my control volume. Okay, so let's understand this. Particularly let's understand the graphical representation of this. First, what is this? You tell me. HV minus HL by XV minus HL. On enthalpy composition diagram, this is nothing but my slope. M into X, and this is intercept. So this is Y, sorry, this is intercept. So this is nothing but equation of a straight line. Okay. Now let's try to plot this equation on enthalpy composition diagram. Say my Dephlegmator is operating at pressure P. So these are my saturated liquid and saturated vapor states for pressure P. Is this one clear? This is X of ammonia, of course, and this is enthalpy. Okay. Now can you tell me what are the states? How I can represent? I will be having some state liquid over here, and I will be having some state vapor over here. The one thing I need to keep in mind that this vapor state must not lie on the isotherm passing through point L. Is this one clear? Because the temperature of the vapor has to be greater in comparison to the temperature of isotherm starting from point L. Is this one clear? Because this liquid and this vapor should not be in equilibrium. Vapor should be at higher temperature. So if my isotherm is represented by this dotted line, then I am representing vapor at this point which is at temperature greater in comparison to the isotherm. Is this point clear? Another important point is the need for Dephlegmator and the rectification column is that at the exit of the Dephlegmator we will be having ammonia rich state. So this point is also clear to us that X3 will be some composition very high value, close to 1. Of course it cannot be exactly 1, but it will be close to 1. Is this one clear? Now the slope of this straight line is HV minus HL by XV minus HL. So this equation is for all these states L, V and state 3. So if this is a straight line, then my L and V must, I should plot it somewhere here, otherwise my line will not intersect. So, or let me place L somewhere here. So this is a straight line in between L and V. Now this straight line where it crosses this X3 composition, that will be my point 3. Will that be point 3 or what will be that point? Please tell me. Will that be that point will be 3? At state 3, ammonia is in which state? Superheated state or saturated state? Ammonia vapor is in saturated vapor state. So at this composition, this will be my point 3. Okay. But what will be this point? Let me consider this point to be any arbitrary point as P1. Okay. All are clear with this point or not what I am saying? This is say some arbitrary point P1. Clear? And this is state 3. Anyone is having any doubt about this? Because whatever ammonia is coming out, that should be in the saturated vapor state. So at X3 composition, wherever it is crossing this line, that will be my saturated vapor state. Okay. Now, liquid and vapor are joining. This straight line is intersecting this composition at some point P1. This point P1 is something which is called the first principal pole. Okay. Point P1 is something which is called the first principal pole, and the straight line joining the liquid vapor is something which is called as the operating line. Okay. So this line joining liquid and vapor is my operating line. Is this point clear? Now let's understand very carefully. What is, let's say this angle is theta 1. If this angle is theta 1, the slope of this line will be simply equal to tan theta 1. Okay, and tan theta 1, for this straight line, slope can be written as HB minus HL divided by. So it means that HB minus HL is nothing but XB minus XL into tan theta 1. Correct? Now, if I write X3 minus XL into tan theta 1, what I will be getting? Like this is my one triangle, I will be having this also as my triangle, L, P1 and this point, that will also form a triangle. So X3 minus XL into tan theta 1 will become nothing but equal to what? No. You see this one? This is base. Base of the triangle multiplied by tan of theta should be equal to perpendicular. So what is perpendicular? This is HL and this is HP1. HP1 minus X3. All are clear with this point or not? Is this point clear? X3 minus XL into tan theta 1 has to be equal to HP1 minus HL. Correct? Sorry. HL. HP1 minus HL. Correct? Anyone is having any doubt about this? Now you see, compare with the previous mathematical equation. What is this HV1 minus HL by XV minus HL? It is slope. Okay, tan theta. So in the previous equation, so it means this right hand side is nothing but representing completely the left hand side. You tell me, this side and this side, are these equal? X3 minus XL into tan theta, same thing, correct? So this must be equal to H3 minus HL plus QD by M dot C. Okay, so HP1 minus HL is equal to H3 minus HL. This distance is H3 minus HL. This entire distance is HP1 minus HL. So this distance must be equal to QD by m dot. Okay. So this distance must be equal to QD by m dot. Anyone is having any doubt up to this point? It is clear. Now let's understand that this is an okay. So typically you tell me what is state 3? It is the state going out of the dephlegmator. For a steady state operation it will be always fixed. Generally for a steady state operation, or let me write it in another way. If I have to simply calculate from here HP1, then HP1 will simply become H3 plus QD by m dot. Is this point clear? All are clear with this point? So H3 is the state at the inlet to condenser, which will be fixed for a steady state operation. M dot 3 is mass flow rate. Again it should be fixed for steady state operation. And whenever you are operating the dephlegmator in steady state operation, then QD must also be constant. So it means that for a given dephlegmator under the steady state condition, HP1 point should be fixed. Is this point clear? HP1 point will always be fixed point. Now, if assume that this LV line is any arbitrary line for any rectifier plate, say some plate, this one. What will happen to operating point which is lying above this and which is lying below this? First important point is clear that my first principal pole is fixed. So principal pole is not going to change. So it means any operating line must pass through point P1. Is this one clear? All are clear with this point? Now for a plate which is above the plate under consideration, one operating point one line can be on left of this and one operating line can be on right of this. Now can you tell me, by considering above and below in the rectifier column, whether above will be left or below will be left? Please tell me. So these two black and blue operating lines are clear now. These must start from point P1. Okay. But for any given plate, say this red line was for this plate. Below will be left. Why? Correct. So the point is, whenever you are entering from bottom, immediately after the generator, vapor will be more heated. Okay. As long as it keeps on moving in upward direction, its temperature will keep on decreasing. In saturated vapor state, high temperatures are towards this side. Okay. So that's why this black colored line. So left side we will be having the below plates and right side we will be having the above plates, then the plate which is under consideration. Another interesting fact which I told you, that the slope of this operating line has to be greater than the slope of the isotherm. All are clear with this point? Slope of operating point has to be greater in comparison to slope of the isotherm. Correct? Because then only vapor temperature will be greater than the liquid temperature. Now we have one additional condition, that at the last plate of the rectifier, at the last plate of the rectifier, my whatever medium is coming out, that should be in the saturated vapor state. Okay, so if that has to be in the saturated vapor state, it means the temperature of liquid and vapor medium of the last plate should be same. Correct? For ensuring that temperature to be same, if you have to do the finite amount of heat transfer, your size of the rectifier should be infinite. That is the reason you cannot achieve 100% saturation. Is this one clear? That is the reason. So, if you are doing separation in each and every plate, okay. So, near the exit of the separation process, your vapor will be pure vapor and your liquid will be pure liquid. So it means if you have pure liquid and pure vapor of a substance present, then the temperature of both cases should be same. If temperature of both cases is same, then in order to do finite amount of heat transfer, your size should be infinite. So because for pure liquid and pure vapor of a substance, you cannot achieve this situation in this practical condition over here, because you are not having infinite number of plates. That's why we are not able to achieve the 100% enrichment. Correct? But ultimately, if that situation is theoretically achieved, then the last operating line must be identical to a isotherm. Okay, last operating line of the system has to be identical to the isotherm. Is this one clear? So there is even one more method with the help of which we can calculate how many number of plates are needed. But maybe I will not discuss that. Okay. So in the next class, we will discuss one more concept, that is about the analyzer and the generator, combination of analyzer and the generator. So typically double rectification is done in the practical conditions, where we use analyzer like our rectifier column only, along with the in integration with the generator, and second thing we use rectifier and dephlegmator. So these are used in the top and bottom combined system. Okay, so that system we will quickly discuss in the next class. After that we will discuss about water lithium bromide system. Okay, and with that our this unit will be over.